everyone. I'm Philip Adebayo. I'm a PhD student at the Department of Mechanical Engineering at the University of Calgary in Canada. I'll be presenting briefly on my research on numerical investigation of vertical borehole heat exchanger of a ground source heat pump system for space heating and cooling in a typical residential building in Calgary, Canada. My co-authors are Charaka Nicholas Fry, Roman Shaw, Abdulmajid Muhammad, and Agwe Imwesigwe. In cold climates, such as those that are found in Alberta in Canada, where the temperature in the winter can drop below -30 degrees C, space heating and domestic hot water production takes over more than 80% of the residential building energy consumption. The cost of natural gas is relatively cheap in Alberta, and basically that also influences the decision where most residents are using natural gas to meet the space heating and domestic hot water needs, which contributes significantly to CO2 emissions. Canada, like any other countries, has set a target to meet net zero by 2050, and the country is interested in reducing the greenhouse gas emissions by 45% below 2005 levels. So in order to meet this demand, there is a need to shift to a low carbon technology, and we need to develop and deploy low carbon energy technologies. So among low carbon energy technologies in FOGI, ground source heat pump is gaining traction as a reliable and environmentally friendly energy solution that can be adopted into the building decarbonization strategy. Basically, ground heat exchanger is the primary and a critical part or unit of a ground source heat pump, and the borehole heat exchanger, a vertical borehole heat exchanger, has been getting relatively wide attention, has been widely studied for ground source heat pump application. So a vertical borehole heat exchanger can be about 60 to 300 meters deep, and then it extracts stable ground energy in order to provide heating and cooling needs with higher heat pump efficiency. It can range from 400 to 600% based on a given location. So why is this study actually important? Climatic and lithological conditions have a huge impact on the performance of a ground source heat pump system. And limited studies have investigated or looked at the performance of conventional borehole heat exchanger in extreme cold climates like Calgary. Generally, in cold climates, heating loads are relatively higher than cooling loads, and this means that the amount of heat that needs to be extracted from the ground each year is greater than what can be injected back into the ground. So this also buttresses the fact that we need to, in the design of a ground source heat pump system, especially the ground heat exchanger, we need to optimally design the system to be able to address the problem or minimize the problem with thermal imbalance. So thermal imbalance basically occurs as a result of differences in the heat that we are extracting and what we are injecting back into the ground. So the purpose of this study is to evaluate the long-term performance of a vertical borehole heat exchanger of a ground source heat pump system for space heating and cooling in a residential building in Calgary, Canada. So we also seek to evaluate the building load capacity of the bore heat exchanger that will be able to minimize the ground thermal imbalance. So in order to meet this objective for this research, we adopted numerical modeling techniques, and presented here is the physical domain of a numerical model. So basically, the numerical model composed of a ground domain. We have the bore heat exchanger, which is a U-tube bore heat exchanger, and we also have the grouting materials. So the depth of the ground heat exchanger considered in this study is 150 meters. And in our study, we ensure that the adiabatic boundary condition is applied on the far end of the ground domain. And on the ground level, the boundary condition is the ambient temperature in that from the meteorological condition in Calgary, Canada. So this is a transient temperature condition that varies hourly depending on the meteorological condition in Calgary, Canada. So here is the building load profile generated from OpenStudio and Energi Plus for a typical residential building in Calgary. And as you can see that most of the time we are extracting heat from the ground, and the amount of time that we have the building load requirement greater than 0 is very minimal compared to the amount of time when we have the building load requirement lesser than 0. So in this study, we consider a vertical U-tube bore heat exchanger that as part of the ground source heat pump system, and we use a water glycol mixture as working fluid. As earlier mentioned, the depth of the bore is 150 meters, and the diameter is 0.1524 meters, which is equivalent to 6 inches. The inside and outside diameter of the U-tube is 32 millimeter and 42 millimeter respectively. So in the computational fluid dynamics model that was developed, so basically the equations that were solved include the mass conservation equation, the momentum equation, and then the energy equation. So basically the momentum equation is solved because of the internal force convection interaction between the circulating fluid and the U-tube wall. So for the building, the peak heating load requirements is about 30 tons. And then the dynamic building load profile was used to investigate the capacity of the bore heat exchanger by considering the total load that is if you are meeting the total building load requirement with a single 150 meter deep bore heat exchanger, and also if you are using the single 150 bore heat exchanger to meet half of the load. So in order to achieve this, and we couple the realistic building energy load with the bore heat exchanger, this is achieved by taking the heat pump unit as a control volume and then perform energy balance on it, where we have also connected the U-tube inlet and outlet temperature. So from this study, we look at the following parameters such as the outlet fluid temperature. We also look at the ground temperature variations at the depth of 80 meters and different points, and also look at the coefficient of performance. So looking at the bore outlet temperature, it is important to mention that the outlet temperature of the ground heat exchanger itself is the inlet into the heat pump, and it's very critical in determining the operation of the heat pump, because most heat pump manufacturer will specify the threshold of the minimum entering water temperature into the heat pump. So the heat pump considered in this case, it has a minimum temperature requirement of 267 Kelvin, which is equivalent to -6 degrees C. So if you look at the outlet water temperature, when the ground heat exchanger is handling 1.5 tons, and when it is handling 30 tons, we could see that in all cases throughout the 5-year study period, we have the 1.5 tons higher, and we do not have any instance where the temperature coming out from the bore heat exchanger is less than the minimum recommended temperature required for the heat pump. But in most cases, for the 30 tons case, we could see that there are times when the temperature of the working fluid is lesser than the minimum pump recommended temperature. So this is for about 28% of the time over the 5-year storage period. So why are we having this? Why is this happening with the outlet water temperature? So if we look at the ground temperature variation at the depth of 80 meters and then at various radial positions. So in this case, we look at 0.5 meters and then 4.5 meters for both 1.5 tons and 30 tons. As we can see, when we are using 30 tons at the point of 0.5, which is closer to the bore heat exchanger itself, so there's potential for ground freezing because we are extracting more than what we are dumping back into the ground, and this explains where we are having minimum temperature coming out from the heat exchanger for most of the time. Though if we look at for the case of 1.5 tons too, it's much better than for the case of 30 tons, but there's also possibility that we continue to use this system. It will also get to a point just like where we are, where the 30 tons case is at the end of the 5-year period. So it's still better off at the far end, especially for the 1.5 tons at the radial distance of 4.5, and also for the 30 tons at the radial distance of 4.5. Is not as worst as around the borehole area, which is majorly our concern to avoid ground freezing. So looking at the coefficient of performance during the cooling season, we could see that the 30 tons cases has higher cooling performance, while the 1.5 cases has lesser cooling performance rather. And on the contrary, during heating mode operation, which is majorly during the winter when we need to extract heat from the ground, so we have the 1.5 load capacity giving us higher COP, coefficient of performance during the heating operation, and we have the 30 tons cases giving us lesser heat performance, coefficient of performance during the heating operation. So in conclusion, why the 1.5 tons case meets the minimum temperature requirement, the outlet temperature of the working fluid is lower than 267 Kelvin for about 28% of the time over 5-year storage period. As you can see from the ground temperature distribution, there is a high potential or possibility of ground freezing in the neighborhood of the U-loop pipe or the ground bore heat exchanger itself, because especially for 30 tons and even for 1.5 tons, we continue to use it for more than 5 years. There's high possibility of ground freezing around the bore heat exchanger. So the cooling COP reduced by 30% and 7% at the end of the 5th year for 1.5 tons and 30 tons, respectively. And finally, although it is recommended that the bore heat exchanger be designed for 1.5 tons, there's also possibility of performance reduction if the system is operated for more than 5 years without enhancement. So it will be important, and this is something that we are looking at in our future study to see how we can enhance the performance of the system. I would like to thank GEOS, Geothermal Energy Research, Energy Simulation Center at the University of Calgary for this opportunity to present at this Energy Summit, and then for the funding support. Thank you for listening to my presentation.